All right, everyone, let's get started. Welcome to ECE 5307, Introduction to Machine Learning. Hope you guys had a good break. This is a strange classroom because some of you are very far away. Some of you are very close. So what I'm going to do today is go through essentially material from the syllabus about how the course will run. And then I'm going to give you a very brief introduction to the kinds of things we'll be doing this term. And then if we have time, we can move on to the first official lecture. So just to start out, the instructional team this semester is myself, and I'm going to have office hours on Thursdays from 12 to 2, both in my office and simultaneously on Zoom. So if some of you can't make it to my office, I'll try to do both. And then we have a TA, Kai-Ying, who's over here. And Kai-Ying is going to grade the homework in the labs, and she's going to do office hours in DREAS 331, and that's going to be not Zoom on Wednesday and Thursday, but then on Friday, she's going to have Zoom-only office hours. So
hi everyone, my name is Kai-Ying Xie, and I'm currently a fourth year PhD student in ECE department. So I'm working on some kind of machine learning problems. And like in particular, I'm working on some clustering problems and do some like more mathematical side of like how to do clustering and do some analysis on how this different algorithm work and converge, something like that. So if you're interested in, like I will hold office hours starting from this Wednesday. So suppose you don't have any questions on homework, you can also feel free to come to my office hour and ask me about anything on machine learning. Or if you have questions on this homework 0 due on this Friday, right? And also like can talk to me, ask me during office hour, because like as like mentioned in the Carmen announcement, like linear algebra is quite important. So if you have like difficulty in linear algebra, you can feel free to come to my office hour this week to like have some review with me. And yeah, so that's
okay. Thanks, Kai-Ying. Kai-Ying was also the TA last semester, so she's very experienced in working with the material of this class. So that's great. I'm very glad and lucky to have her again TAing this semester. So our objectives this semester, basically you could say there's three big things. We first want to understand what machine learning is. We want to understand at least a few ways it can manifest. These are some of the main problems that you see in machine learning: regression, classification, clustering, dimensionality reduction. We also want to understand this from two different perspectives. The first one is the mathematics behind all these models and tools and so on. And second, we also want to know how to use those tools. And I would say it's not really enough to know one or the other. Like if you take some theoretical course in machine learning, you learn all this nice stuff, and then you can't do anything with it, that's a big limitation, right? Or if maybe some of you have already played with code out there, and maybe you can already do some stuff, but if you don't really understand what you're doing, it's hard to do it well, and it's hard to move forward and do bigger things. So we also want to understand what's behind all these models, and for that we need to really understand the mathematics. Mathematics is just the language of engineering and computer science and all that. That's how we express ideas. So those are the two main things we want to work on this semester is understanding the ideas and then understanding how to implement those ideas. So we're going to be using Python-based tools, things like NumPy, scikit-learn, Jupyter Notebooks, PyTorch, GitHub, and so on. Okay, so in terms of prerequisites, if you're an undergrad, you have to be an ECE major, but if you're a grad student, you can come from any major. The prerequisites, in some sense, are pretty low level. We're just looking for calculus and linear algebra. So at Ohio State, this would be, and these are, I think, required courses for ECEs, these courses here, these math courses, and then some basic probability and statistics. And we're going to do a little bit of review of some of the probability and statistics stuff. We're not really going to be doing any review of the linear algebra during the lecture. The linear algebra is super important, and so the way we're doing the review is through an initial homework. I'm calling homework 0, which is due this Friday. And there's also going to be a Carmen quiz, just a multiple choice quiz, which is also going to be due on Friday. And I really want to emphasize how important the linear algebra is, because I've taught this course a bunch of times, and what I always hear from students later in the semester is, wow, I didn't realize how important that linear algebra was going to be. And now I'm lost because I can't really understand any of the lecture slides because they use all this linear algebra and I can't really understand linear algebra. And that's the biggest reason that students drop the course. So, so it's really important. You do have some time. If you feel like your linear algebra is rusty, you do have some time to review it, to practice it, to get better. Especially this week of the course or the semester, you're probably not inundated with other homeworks and stuff, right? So you have some time now. As the semester goes on, you're going to be more and more busy. It's going to be harder and harder to learn this stuff. It's going to be harder and harder to catch up on all the stuff you didn't learn or couldn't learn because you couldn't understand the language, the linear algebra in which it was presented. So I really want to enforce that or emphasize that. So again, there's this homework 0, and it's based on a handout, a really nice handout that was written by someone at Stanford that's relatively short, concise. It contains just the stuff you need and not really any more, but not any less. I don't want you to go and feel like you have to learn a whole book on linear algebra because you simply don't have time to do that, right, in a week. But at the same time, there's certain things you need to know in order to be successful in this class, and they are available in this handout. The handout, you can access it once you get access to the GitHub repository. I'll be talking a little bit more about that. There's been some important announcements on Carmen, so please read all those announcements carefully. But that's the kind of the gateways. You first need to get access to this GitHub repository for the course, and then you can see this this handout and the lecture notes and all kinds of other stuff. Okay, and then in terms of prerequisites for programming, like I said, the course is going to be based on Python tools, but I'm not assuming that you know Python already. So you just need to know how to do some sort of high-level programming. It could be MATLAB, it could be C or C++. And with that, that's enough to learn Python, because Python is not that different from those other tools. It's not that different from MATLAB. So by doing the labs in this course, you will just gradually get better and better at Python, even if you've never seen it. And hopefully by the time you're done with this course, you'll feel pretty comfortable with it, and you'll feel like you can go off and do your own projects in Python. Okay. All right, so this is an in-person course. I'm going to be lecturing in this room, 4 o'clock every Monday, Wednesday, Friday. I do expect you guys to attend. I think it's really important to be able to be here and ask questions. I will be recording all these lectures and posting them on YouTube. So if for some reason you can't make a lecture one day, you can find the YouTube video. Also, you can watch the YouTube videos, again after lecture, or maybe if there's something you didn't catch, you can watch it a couple times. Students have told me that's really helpful. That's why I keep doing this. In very rare cases, if we need to do lectures online, there is a Zoom link I set up. The lectures will have some blank lines in them where I left them blank so that you guys can fill them in, because I find that if the notes are completely filled in, it's easy for you guys to your attention wanders away. But if you have something to write down, it helps you stay grounded and active. And my intention would be that you guys come here with either a paper printout or a tablet or something with, something that you can write on and take notes on, because there's a lot that I'll say that's not exactly in the notes. Maybe I'm talking about some figure and talking about specific things. If you can write those things down rather than just trying to remember everything in your head, that could be that could be better. And also, the more you write, the more you stay engaged in the lecture. That's super important. So when you're looking for help, if you're working on homework or lab, or if you're just reading the lecture notes and you have a question, in addition to the office hours that I already talked about, I've set up these Carmen discussions. And this is just like a discussion board on Carmen where you guys can post a question and I can answer it, or Cayenne can answer it, or you guys yourselves can answer it. And this is especially helpful like when working on the labs, which are all computer-based. You guys have the ability to come up with really weird errors based on very particular things you do that's hard for us to figure out how did that happen. But it's often the case that some other student did the same thing and then figured out, oh, well, it was because I did this weird thing and here's how to fix it. Or maybe you have some very specific thing to your operating system that I don't have on mine, and so on. So those discussion boards are very useful. Also, students can often get to those answers quicker than I can or Cayenne can. So I encourage you guys to be active and to be responsive on those discussion boards, and it makes it a little bit more fun too, I think. Okay, so in terms of how the course is going to be graded, there's 5 components. Each are worth 20%. So there's going to be weekly homeworks. So every Friday you can expect a homework due, except for the weeks where we're having a midterm. The midterms will also be on Fridays. There's going to be 2 midterms. And the dates, these are the dates. So please put them in your calendars. Don't come to me a week before the midterm and say, I didn't realize a midterm was going to be this day because I have this other thing. So I'm telling you guys right now exactly when the midterms will be so that you can schedule your other things around them. Okay. Also on Fridays, due at midnight, are weekly coding labs. These are labs that you can do completely yourself. You don't need to go to any room to do them. They're going to be, like I said, Python-based, Jupyter Notebook-based. The way it's going to work is that you're going to find an invitation on Carmen, which is going to contain a link. You're going to click that link, and it's going to bring you, let's see, what's going to happen is it's going to create for you a repository on GitHub. And that repository is something that you can pull down to your computer. You can complete the lab, and then you push it back up to the cloud, and then the TA or I can get access to your solution. And we do this with GitHub because Carmen does not have a good way to deal with these coding assignments. GitHub is a great way. And also GitHub is the way that everyone in the machine learning world exchanges code. So if you start to do stuff with machine learning, it's just GitHub is something that you need to learn. So it provides an opportunity to do that. So that's the weekly homeworks, weekly labs, and weekly Carmen quizzes. These are just multiple choice, 5-question, 7-minute quizzes. There's something special about this first quiz, quiz 0, which is that I'm giving you guys 5 attempts to do it. All the other quizzes, you'll just get 1 attempt. But for this first quiz, I really want you guys to be able to practice. If you take the quiz and you see that you did really poorly, I want that to be a feedback mechanism that says, okay, I need to go and work with this stuff a bit more, and then try again, and try again, and try again. I don't want you to just get discouraged like, okay, I did terrible in the quiz, and I suck at linear algebra, and that's just the way it is. Because that's not a good solution. I really want you guys to work on it and practice and get better. So first quiz, you have 5 attempts. Whatever the most recent score is, that's the one that will count. Okay? But at the end of the day, or at the end of the week, Friday at 4 p.m., that's when that's all due. Last thing is there's going to be one final project at the end of the term. I think I have, yeah. I'll talk about that on the next slide. But basically, with all this stuff here, you're going to get, every one of your assignments will be graded on a point scale. There'll be no letter grades until the very end of the quarter, or end of the semester. So to see how you're doing midway through the semester, I'm going to be posting histograms. You can see where you stand relative to your peers in terms of all these components, the homeworks, the labs, the quizzes, midterms, and all that stuff. Undergrads and grads are going to be graded on different scales, so I'll be posting different histograms, or let's say different curves. And then finally, at the end of the semester, you'll have one cumulative number score between 0 and 100, and I will eventually map those numbers to letter grades at the very end of the term. Okay. So the final project, the goal will be to apply what you've learned in this course to a data set. What the data set is, I'm going to get a data set from somewhere, some real world data set. I'm not going to tell you what it is, but that's not really important. That's not the way machine learning works. The way machine learning works is you're given a data set and you learn the data set. You learn about the data set from working with the data itself. You don't have to have an expert tell you this was data from this application. Okay, so you'll be given this data set, a design objective like minimize the classification error, something like that. And you're going to use the techniques you learned in this course to try to do that task as well as possible. There's going to be an in-class Kaggle competition where you guys will be competing against each other. You'll be working in teams of 3. You guys can choose your teammates if you like, or if you feel like you don't know people in the course, that's fine. We can put you together in teams, or maybe there's 2 of you and you're looking for a partner. We can help with that. These details we won't worry about for a few weeks. We'll kind of get into the project in, I don't know, maybe like six weeks or so. We'll start talking about the project. But finally, what you'll be doing with your final designs, you'll be explaining them in a written report. You'll get graded based on the quality of your report as well as the quality of your results and how well you did in the Kaggle competition. Okay, so there's no required textbook for the course. I'm not going to be following any textbook. These are just 4 textbooks that that I think are somewhat useful. There's more and more textbooks for machine learning, so there could be other ones out there that are good too. But one of them that's kind of a foundational book on machine learning is this one. It's a famous one. It's probably the best one for the theoretical ideas. The trouble is all the code examples are in R, which is a statistician's language, not Python, so it's not useful for that. So if you're looking for a book that's just great with a summary of Python commands for machine learning, this is one. There's another book which I think is a nice combination of code and theory and concepts, which is this one. The trouble is that, so we're going to use scikit-learn for much of the course, but when we get to the deep learning stuff, we're going to be using what's called PyTorch, whereas the problem with this book is it's written with TensorFlow, which is sort of a competitor, so it's not directly useful for our machine learning coding knowledge, and that's where this very last book comes in. This is the PyTorch, official PyTorch book written by the PyTorch authors, and so this is a great reference for PyTorch itself. But you don't need to read any of this stuff if you don't want. The course notes should be enough. And throughout the course notes, anytime you see something in green, like this or this or anything, that's a hyperlink. You can click on it, and it will take you to whatever website that is. So a lot of times, if I'm explaining something and I'll just put in a hyperlink to what I think is a great source for just a short background on that. Often it's a Wikipedia page. There's good Wikipedia pages for a lot of machine learning stuff. So, so that it kind of acts like a textbook there. When you want more detail, just click on the link, read that detail, and then come back to the notes. Okay. So as I mentioned, we're going to be doing some stuff with Carmen. We're going to be doing some stuff with GitHub. So the stuff we'll be doing with Carmen, Carmen announcements, like I already posted a bunch, these discussion boards I mentioned. The homeworks will be exclusively based on Carmen, so you'll find a PDF of the assignment. You will upload a PDF of your homework to Carmen. The labs, what you'll find on Carmen is the link to the GitHub repo, but then everything else will be done through GitHub. You'll still find solutions and histograms on Carmen. Quizzes, multiple choice quizzes will be on Carmen. Exam solutions, practice exams, those will be on Carmen. Final project instructions will be on Carmen, but your code will be submitted through GitHub. And of course, you'll find your grades and those histograms on Carmen. Okay, so what are we going to use GitHub for? So GitHub is where I'm going to put the lecture PDFs. And you'll also find demonstration code there. So each lecture will come with one or more pieces of code to demonstrate the concepts. These will usually be in the form of Jupyter notebooks, which I'll talk about in a second. And as I mentioned, you'll be submitting your lab code through GitHub as well as your final project code. This is where most of the course materials will live, in that repository. I posted some instructions for how to get access to that in one of the announcements, so please go through that. I saw that a number of you have gotten access, which is great, but if you haven't, please do that soon. So just to talk a little bit more about GitHub. So when you look at this course repository, let me just go there right now. Let's see if it will take me there. I might have to log in. Okay, so here's the course repository. So it has a bunch of information here that has like the YouTube link, the Zoom link, blah, blah, blah. But this course outline is going to grow as we go through the term. You're going to see, with each new unit, you'll see you'll see the lecture. This is a PDF of the lecture slides. This is a demo of the code. So if I click on the lecture slides, which is a PDF, the nice thing is GitHub will render them for you in your browser directly. Also, let's see. If I click on the code, so let me click on this. Here you'll see a Jupyter notebook. So this is sort of a combination between code and text. You can see some stuff formatted as text, but you can also see these code blocks. And you can see basically what happened when the code is run. Now, if you actually want to run the code yourself, you have to pull this down to your local machine or some other machine in the cloud where you can run it. So here we're just viewing it. That's all we can do here is just view it. But it's nice that you can view it directly. You don't have to like fire up your Jupyter notebook app to view it. You can just view it in GitHub directly, but you can't run it. You can't try something new. Okay. So just want to emphasize to keep current in the course, if I change, when I add new lectures, if you want to get access, you need to pull that down from the cloud to your local machine, and then you can get access to the latest stuff. Okay, so just a few words on Python. We're using Python because several reasons. It's a general and powerful language. It includes many machine learning libraries, especially for deep learning. I would say for deep learning, it's definitely the main language that everyone uses, and it's free and open source, unlike MATLAB, which is really expensive once you're out of school. Also, MATLAB just doesn't have that much machine learning stuff on it. Okay, like I said before, no Python background is assumed. We'll teach it to you, but you just need to know basic programming. And now if you want to practice a bit, if you feel like you have some extra time, I did include on that primary course repository, there's tutorials about Python in general, about NumPy, which is sort of like the linear algebra package in Python. There's a few tutorials that if you feel like you're good at MATLAB and you want to know, like, how do I go from MATLAB to Python, people have written about exactly that. And then practice materials. If you just want like 100 problems in NumPy, I gave you several sites there. You can practice it. So we'll be using, these are some of the libraries we'll be using here. And so one way to get Python on your local machine, the way I recommend is using this Anaconda distribution. It's pretty straightforward. What we do in the course with our demos and labs will not require huge computational resources. You should be able to run everything fine on a laptop, even a not powerful laptop. Once you get to the project, though, you might want some more computing power. And so there's lots of good cloud resources where for free you can run a certain amount of stuff, and then you can pay a little bit to run more. There's many different ways to learn about how to access those. Here's a few links, but you can find many more. I already showed you one of these Jupyter Notebook demos. So in the course notes, there will be screenshots of them to try to kind of complement the lectures. We want to understand not only what we're doing, but how to do it in Python. And so already for this linear algebra review unit, there's a couple demos on NumPy, which is the Python linear algebra package. And yeah, so that's it for sort of syllabus level stuff. Are there any questions on anything about how the course will be administered? No? Okay. A lot of info there. No questions? All right. Okay, so then let's talk a little bit about the course material. Just sort of an introduction, what is machine learning? So there's just a few slides here. So first we want to understand what we might want to accomplish. What are some examples of problems that are machine learning type problems? And so these are three very generic problems that are common. You see them in many fields, not only engineering, but also science, medicine, business. So the first one, which is the one we'll start out with in the course, you can think of it as prediction. Statisticians call it regression. I'll be talking about this in just the next slide, I think. Classification is another one, and something that might make sense as categorization, but it's technically referred to as clustering. These are three examples, three of the more common examples of machine learning. Machine learning is definitely more than this, but just these three things get at the heart of many, many machine learning problems. So let's talk first about this prediction or regression task. And I'll just introduce this just using one very simple example. So suppose that our goal is to predict a future stock price based on current and past data. And so when I say data, I'm being very generic here. This data could be past stock prices, but it could be a lot more than that. It could be today's weather, it could be news articles, it could be many things. But our goal is to predict, let's say, tomorrow's stock price so that we can make a good investment. So one way to approach this, what you could call maybe the traditional way to do this, would be to build a mathematical model of the stock market based on some economic theory. But as you can imagine, this doesn't really work that well, right? Because if it did work that well, then everyone would be rich, right? So instead, so we'll be talking about examples of different approaches, but the overall goal is to do some prediction based on current and past data. So you could say maybe the general thing is estimate the value of one or more quantities given measurements of related data. Okay, what about classification? So here's an example. Suppose that I want to recognize a handwritten digit from 0 to 9. So here are some pictures of these handwritten digits. So these would be zeros, these would be ones. You can see there's a bunch of twos and so on. So you could think again, how should we approach this? So you might say, well, okay, I know conceptually what a 0 is, what a 1 is. Even if someone gives me a picture of it, I know that zeros are circles and ones are lines. But actually, if you think about it deeper, it gets kind of tricky because you can see examples of maybe borderlines between a 4 and a 9, which is just when that top thing is closed. So at what point is it a 4 and what point is it a 9? It's not exactly clear. Yeah, the more you think about doing this based on some like symbolic notion of a hand-drawn 6 is exactly this, it's actually quite difficult. But somehow, we as humans are pretty good at this. So how did we learn how to do this, right? That's sort of a question. But hopefully you can see the general problem is what we want to do in classification is identify the category of a quantity given measurements of related data. So the difference here between regression and classification is here, we're identifying a category which is discrete, right? Whereas over here in regression, we're estimating a value which could be discrete or could be not. But the difference between values and categories is that values are ordered from small to large, whereas categories are not. Cats, dogs, planes. Can't say like a plane is greater than a cat. It just doesn't make sense. Those are categories, but numbers you can compare. So the difference between regression and classification is you're doing a prediction, trying to predict something, but in one case it's a value, in the other case it's a category. Okay, those are two examples of what people call supervised machine learning tasks. So one that would be unsupervised is known as clustering, or you can think about it as categorization. And I'll just give you one example. Let's say you have this collection of many text documents, just a big jumble of these articles, and your goal is to categorize them. Put them together in sets where within each set there's similarities between those documents, but across sets there's differences. If we view this not in terms of text documents, but just in terms of pairs of numbers, if I give you a pair of numbers and you want to say, is that pair of numbers different or similar than another pair, that would be like this picture. So here we have, like, let's say x1 is the first element of the pair, x2 is the second one. And as a human, when you look at this, you can say, oh, okay, yeah, these seem to be one category cluster. These seem to be other ones. You can kind of do this. So the question is, how do we do this more generally? How do I do this with text documents? What are all the details here? But at high level, what you could say is that the goal here is to partition a given data set into distinct groups such that the data is similar within each group and different across groups. So key questions here, how do you define similarity and difference? And then as well as how do you do this? How do you do the actual clustering? Okay, so those are some examples of the tasks we want to perform. Are there any questions on any of these tasks? Okay. Next, how do we solve these tasks? So, as I alluded to before, we could say the traditional approach, maybe what people did 50 years ago, is when you want to perform a task, you find some expert in that task. Maybe it's a scientific task, so you find a scientific expert. They know all these theories. They know the physics, whatever. They give you a model, and then you apply the model to the task. And in some cases, that works great. Like, let's say you want to design a circuit. Have things like Ohm's law. We have all this knowledge about circuits, how the different components work, how they work together. That works really well in most cases. So this traditional approach is definitely useful in a lot of cases, but it's not always useful. Sometimes it fails. So for example, in some cases, we don't have a good scientific model. Let's say we're working with the stock market. No one really knows how it works. Some people have some inklings better than others, but no one fully understands it. Or you might have a case like in acoustics where there's good models, but if you want to do something like noise cancellation, in some sense that's just an acoustics problem, but the complication there is that there's so many variables that you would need to know in order to apply the model. So if there's this weird noise coming from somewhere outside, and you have some noise canceling headphones, or your objective is somehow to cancel that noise, you would need to know, first of all, where is that noise coming from, maybe something about its spectrum, maybe something about all the reflecting surfaces in this room, including all the people in this room. And if you could know all that stuff, you could easily figure out how to cancel that noise, but all that stuff might be changing. Maybe the location of the noise is changing, so it's difficult to apply those models. So instead of trying to apply the model, maybe what you want to do is just come up with some system that somehow learns. It comes up with maybe some cancellation network that has a whole bunch of parameters in it, and it just learns how to adjust those parameters so that somehow that noise is attenuated. That's the learning approach. That's an example of machine learning, where basically you just build a model based on seeing many examples of the data. That's all you need to know. You don't need to have any scientific expert tell you this is how it works. You're just given a whole bunch of data and you figure it out. Okay, so it's very powerful, very general. Yes?
Could you say that specific example there would be supervised or unsupervised learning on the specific problem?
It kind of depends how you formulate it, but I think the easiest way to think about it is, if you look at how a lot of the, let's say, headphones work or earbuds, they have one microphone that is measuring sort of what you want to hear. Let's say one source that's the desired. This is what you want going in your ear canal. And they have another one, let's say on the outside, that is measuring the noise source. And they basically say, like, we want to make sure that what's going into your ear canal is decorrelated or somehow doesn't have any contribution from that noise source. And if we can remove that, we're pretty sure that what's there is going to be good. So in that case, you have kind of like a reference that you want, and then something else that you don't want, and you have all these parameters that you control to, so that the target, so that the solution that's measured inside your ear canal is close to the target. So to me, that has a supervised flavor. But there are actually ways to approach it that are more unsupervised in nature. So it is kind of a debate. Yeah.
And what an unsupervised example would be like trying to categorize desired outside noise versus undesired outside noise? Like if you want some kind of pass through?
It's a little bit hard to describe the unsupervised viewpoint because it kind of gets into a whole bunch of details. So I can't kind of go into the depth. But I did actually recently have like a PhD student in that field, kind of tell me about like here's like different definitions of supervised and unsupervised, which seem to both work if you think about them in a certain way. But great question. So I don't know if that answered it, but we'll be learning a lot more about unsupervised and supervised as the course goes on. Most of the course will be supervised. We'll get to the unsupervised stuff towards the end. Okay. All right, great. Any other questions on anything so far? Okay, so we learned a little bit about what kind of tasks we want to perform. And now let's talk about how we actually do this. So here it's going to get a little bit technical. It's absolutely fine if none of this stuff makes sense. The goal is that by the end of the term, you'll look at this and you'll be like, yeah, that's exactly it. Okay, so here are the key ingredients of machine learning sort of from a mathematical perspective. First of all, we want to have some sort of modeling function. In the case of supervised learning, you can imagine this as your prediction function. So you put the thing you're using to make the prediction inside it, and then it outputs the thing you're trying to predict. So this function is going to depend on a whole bunch of adjustable parameters. In the case of neural networks, this could be millions of parameters. In terms of the simple things we'll start with in Unit 1, it's going to be 2 parameters. just to understand things in a simple way. But that's the modeling function. Now we need a loss function. The loss function is basically just a way of measuring how well our model is performing. The loss function could be something like mean squared error, something simple like that, or it could be a lot more complicated. We need a training data set, which is a whole bunch of data on which to evaluate our loss. We want to know when our model is performing well or not well, and we can test that based on a lot of data that we've collected. And finally, an optimization algorithm, which is an algorithm that is able to adjust these parameters theta so that the loss is low on that training data set. So it's kind of putting everything together. So, so for example, maybe just, let's see, do I have an example here? Yes, so here's an example with stock market prediction. So we can call the future stock price Y. Let's just imagine that's a real number. We're going to be using currently available data. This could be very generic data. Let's just imagine that it's D real numbers that we stack together in a very long vector. The modeling function, F, is going to take in X and output an estimate of Y. The modeling function could be a deep neural network, or it could be something as similar as a matrix multiply, something like that. And in this case, the loss function, we want that to measure the accuracy, how close our prediction is to the truth. So squared error would be one natural candidate. Absolute error could be another one. We need data, many examples of X, Y pairs. So for this, we would go back in time. Let's say we were using, for a given day's stock price, maybe we use the stock price in the previous 10 days, let's say. So if we're doing that, we would need let's say today's stock price, this is for training, we use today's stock prices and the previous 10 days, and then we can go back a day. Yesterday's stock price and then the previous 10 previous to that, and go back another day, 2 days ago stock price and the 10 previous to that, and so on. So you get many, many, many examples. And once you have enough examples, you're ready to apply your optimization algorithm. So this is sort of in one big equation, putting everything together. So here's our model, which depends on some parameters theta. We're trying to adjust those parameters. Here's the input, and this is going to be the ith input to our prediction. This is going to give us, I'm calling this yi hat. The hat means it's a prediction of the true yi. We're using this loss to quantify how close those are together, how successful y hat is at matching y, and then we're summing that over all our training examples. So this is our overall loss we're trying to minimize. We're trying to find the theta that does the best job at minimizing that loss, and we're going to call that theta hat. Okay, so just a little bit of notation here. How many of you guys have seen this argmin? Does anybody know what that means? Okay, so when you think about the minimum, let's say I have a function, and I'm trying to minimize that function. The minimum, I'll call this, let's say, jx. X is on the horizontal axis. This would be the minimum value of j. It's the height of the bottom. But there's also the minimizer. This value, this is the x at which you attain the minimum. This is what we mean by argmin j x. So we can call this maybe x hat. So this is the one that's minimizing the function. So we have the minimizer and the minimum, two different things, right? So sometimes we have the arg there, which means we're looking for the minimizer. Sometimes we don't have it there, which means we're looking for the minimum value. Is that clear? Okay. Okay, so once we do this optimization, we finally get a theta hat. And now we can plug that into our model, and now we can actually use this. We can go to some new X we've never seen that's not in our training data set, and we can predict this. So this is maybe all the information we have today, and then we can make a prediction about tomorrow's stock price. Okay, so this is sort of putting everything together. So it's okay if this is a lot not making total sense. We're going to go through very slowly throughout the semester and learn all these components. Okay, any questions on this slide? All right, so, okay, what are we going to learn in this course then? We're going to be learning many different ways to design that modeling function. We're going to start out with linear models, polynomial models, eventually work our way up to neural networks. We're going to be learning about many ways to construct that loss function. We'll start out with just simple, like, let's use a quadratic loss, and eventually we'll come up with some statistical interpretations based on maximum likelihood, maximum a posteriori. We'll learn about using kernels. We'll get into constructing algorithms to do that optimization, like stochastic gradient descent, or Miho rule, and so on. And we'll be applying all this and learning all this for tasks like prediction or regression, classification, clustering. And that's just sort of like the skeleton. As we go through, we're going to be learning about a lot of other useful and important concepts of generalization, which basically means, like, if you have trained a model on some test set, trained it on some training set, is that going to, and you get good performance there, is that going to mean you're going to get good performance on some test data that you haven't seen? What kind of things can we do to try to make sure that it generalizes better? So we'll be learning all about things along that vein. We're learning about regularization, ensembling, which is when you combine many different simple models together to get a more complicated model, more intelligent model. Principal component analysis, non-negative matrix factorization, Gaussian mixture models, expectation maximization. So a lot of good things that have a lot of applications even outside of machine learning. And again, the main things we're trying to learn concepts in mathematics on one hand, but also how to implement them on the other hand. And like we said, we need linear algebra, statistics, and some sort of coding. Homework 0, again, is going to be all about linear algebra. Please try to give it some effort. And the coding should be pretty easy. All the students tell me that the labs are, even if you don't know Python, it's pretty easy to learn the coding from the labs. My last comment is that this is not an easy course. As you see, there's a lot of deliverables, right? Every week, homework, lab, quiz. So if you're a student that just was looking for an easy course to add to your schedule, it might not be the right thing. If you're really interested in learning about machine learning, I think this course is great. The students, many students have told me that the students that came here really wanting to understand machine learning have told me they loved it. But it does depend on a certain amount of facility with linear algebra. So if you are feeling rusty, now is the time to catch up. So those are the main things I wanted to get across today. Are there any questions on anything? No? Okay. If you guys have any individual questions, feel free to ask me now, or Kai-Ying will stick around for a little bit. And hope you guys stay in the course, and we'll have fun learning about these concepts. Oh, question?
For the first midterm.
First midterm,
On
yep.
the announcement, it says February 17th,
Okay.
and the slides, it says February 7th.
Oh, okay, so somewhere there's a typo. I can look at my calendar. Thanks for noticing that. Let me see, I'll tell you which one is correct. Just a second. Yeah, so it's the 17th. 17th is Friday, thank you.
Excuse me, sir. On next Friday, we have a qualifying exam. So we have homework and activities next Friday.
What do you mean by qualifying exam?
For the PhD qualifying exam.
So you're from a department where everyone has it on the same day?
No, we have the 2 exams on the next Thursday and Friday. So it's overlapping with your homework and
Which department are you in?
mechanical.
I see, yeah. Yeah, I mean, like in electrical engineering, the qualifying exams is different for every student. So, yeah, unfortunately, I can't really change this course. I don't think there's too many of you mechanical students here.
At least
2 of you, but there's like 70 students in the course. So,
it will be very difficult for us to do that quiz and submit homework on 20 because we have written exam on 20.
so you get the homework assigned a week in advance. So my recommendation is just start early, finish everything for this course on the weekend.
The homework one, it should be a handwritten or
Either are fine. All you have to do is have a PDF at the end of the day, upload a PDF. So you can handwrite it or typeset it, however you like.
Thank you.
I don't know who was here first.
My question is very short. I don't have experience in coding at all. I just started this field.
Okay.
Do you think that would be very hard if I don't have any experience in coding?
It's a good question.
I'm in a structural engineering program. I always deal with like mathematical stuff, structural analysis, or something like that.
Yeah. I've never had a student that hadn't had coding, so I don't know. I would say, yeah.
Can I get myself like ready on YouTube or something?
Yeah, like there's, so in that GitHub page I mentioned towards the bottom, there are all sorts of practice things that I included. So those practice materials could be really useful
So
to you.
knowing fundamental things about coding is enough, or I just need to be
Yeah,
expert
just having, knowing basic coding is enough. The details, I think, are what you can learn. Yeah. So try it and see. I don't know.
Thank you.
Sure.
I did a first attempt at the quiz
Yeah.
earlier, and it didn't show the grade or anything afterwards. So
Right.
it was like needed to be graded
Oh.
still. I didn't know if that was a mistake or if it would open later and it would just show the grade.
Okay. So it didn't even report your final grade.
No, it said that the instructor saw to grade it. And it just said,
Okay.
it gave me the option to try again, but it said that.
I'll have to see, because I can't like release all the answers, but
Yeah, of
at
course.
the same time you need to have some feedback.
Yeah.
So let me see how it's configured. Thanks for letting me know.
Do we have any quizzes or labs draft or something like that? Like,
I usually drop the lowest quiz and the lowest lab and the lowest homework at the end of the term.
the other question was, I'll be graduating this semester, so like I heard like many people ask you to come up beforehand. So like, do I have any procedure for that or does
No. I'll get the grades in time.
Thank you.
Two major questions. For the homework 0, is it okay to show up to office hours asking questions on some of that stuff?
Sure.
Especially since as a learning algebra review, it's been a year
Yeah.
since I took it. But
Yeah.
Okay.
Yeah, like Kai-Ying will be in office hours all week, so
Okay.
yeah, no problem.
And the second is I'm also taking the capstone this semester and might demand like me going to Honda, like their lab and missing a couple of days of school. In those situations, if that overruns some deliverable, could I negotiate something that they have?
So all our deliverables are online, so, and even the lectures, you can watch them on YouTube, but everything is submitted online, so you shouldn't need to be here physically for any reason. Should work out fine.
Just worried about my workload this semester again. because
Yeah,
I
the
took that-
workload is another question.
Yeah,
but-
I took that last semester and oh my god, so much time.
Yeah.
But I will try to make it work.
Okay, all right, good luck.
I just had a quick question, kind of basic. So I didn't quite get the difference between the classification and clustering thing. I mean, the words are, if you find synonym, they're similar to each other, right?
Yeah, so in one case, you're predicting, you could say an ordinal value, like a number. In another case, in the classification case, you're predicting a category, like cat versus dog. So if I show you like an image and I say, is this a cat or a dog, it's a classification problem because it's like there's two different categories and you're trying to figure out which category it's in. On the other hand, if I say, what's the value of this stock tomorrow, that's a number, right? Or if I say, what's the Amazon rating of this product? even though that's discrete, like 1 star, 2 star, up to 5 stars, it's still like an ordered value. If I tell you it's 4.2 stars, you can still understand what that means. So that's basically the difference. So we're going to start with regression, and then we're going to learn why those methods don't work that well for classification, and then we're going to focus on classification. But we'll slowly go through these.
Okay, so I was kind of confused between classification and clustering.
Oh, okay.
Second and third.
In classification, we have pairs of the features, the things we're using for the prediction, as well as the target. Whereas in clustering, we have no targets. Like, I just give you a bunch of points or a bunch of documents, and I've not told you, like, this should be a sports article, this should be a science article. I have no idea. So it's like up to you to kind of create the class and the
classification features
Yeah.
based on which I'll just.
like it's up to you to come up with the categories.
Wednesday and Thursday will be
Whereas in classification, someone has already said, these are the categories. Now tell me which,
meeting room.
this document, which category should that be placed in?
Okay, that's cool. Perfect. Thank you so much.
Sure. Hi. Oh, all good?
Yeah, other.
Okay.
Thank you.
Sure.